Today we're going to see this concept of the root locus plot and what it means and how this helps us in designing a control system. So let's take a look at the system on the screen that describes basic system and a unity feedback. So what we have in here, as I mentioned, is that you have this is your system. It could be a motor, in this case control motor, where you want to control the angular velocity or the position, and this is your measure here. So you measure and then you compare it to a reference, which would be a position or velocity. Once you compare it, you come up with an error. You need obviously to correct the error, and so you design the controller here. And in this case, this K indicates a proportional control because it's just a constant. So the more error, the more control. So that we feed back into our system, and it's a closed loop system, you see. So Professor Evans in the 50s, he came up with this idea that if you know a transfer function and you build this loop around it, by knowing the basic roots of the characteristic equation of the system, or rather the denominator of the transfer function, but the roots of the denominator of the transfer function, you should be able to predict how you could design this control system. That's the concept of the root locus. So let me show you some of the pictures in here that indicate how we can look at this. Okay. There we go. He is saying that if you have let's say a transfer function like this, the roots of the characteristic equation, in this case it has 2, because if you equate this to 0, the denominator, obviously s is 0, but s is minus a also. So you have this this plot, and then as you vary k, you could find out where this plot will intersect this axis. So the root locus plot is made with an imaginary plane. So this is the imaginary side, the S plane is called the S plane, and to the left is remember how you plot complex numbers like this. So in here you have one of these plots, and where this crosses is the limit of the stability of the system. The roots of the characteristic equation, or the roots of the denominator of a transfer function, are also the natural frequencies of your system. Okay. So Professor Evans came with this idea that if you have this transfer function, and it doesn't matter how you obtain the transfer function, we have seen during these lectures that you could obtain it using the block diagram method, but also you could obtain it using the bond graph method. So right now we are beyond producing those, and we will concentrate on a system that just has this transfer function like that. So we could just go directly into MATLAB and take a peek with a transfer function like this to see what we have in here. For example, well, why don't we just do that? Let's propose a system in here in our notes that would be like that. Let's just say we like I said, at this point we just work with the transfer function. So why don't we, so that you remember what this is about: root, locus, plots. Right? And our transfer function, we're going to call it g of s, which is our transfer function. Let's say it's 1, and as I showed you in the slide, it would be like s times s what do you say, s plus 2, I think it was, s plus a. So let's say s plus 2. How is that? If you take this denominator here and you say s times s plus 2 equals to 0, isn't it true that s is equal to 0, but also s is equal to minus 2? Minus 2. Just make sure that we do it right. S is equal to minus 2, like that. So how do you plot this? Here, if you plot this in the S-plane, like this is a S-plane. This is the imaginary side, this is the real side. Alright, so s equals to 0 is going to be right here, right? But this minus 2 is going to be something like here, minus 2. And so this is s1 is equal to 0, and let's say s2 is equal to minus 2. So let's put it like this: s1 and s2. What Professor Evans is suggesting is that we use this transfer function and we use a basic test that we can apply to a system. This is my transfer function, which is 1 over s times s plus 2, like this. And then we have a feedback, a unity feedback, that will be compared to a reference point. And what he's saying is, you know how we do like a step input, we do impulse input. This is just like another test to design controls. So he is saying, if we build this loop around my system, and this loop is a unity feedback like this, yeah, this is your reference, and this would be your error in here, because this is the signal. Like, for example, let's say this is omega, or let's just say up, O, because up at the base. So what we can do is, the test, it says, make a test of the possible, yeah, we say, why don't we just say this, find possible roots of s times s plus 2. This of course is equals to 0. Is like writing s squared plus 2s plus 0 equals to 0, like this, right? This is the same thing. Find the possible roots of this if k varies from k equals to 0 to to k equals to infinity, and make a plot. You can say, when say I'm going to put and make a plot of where those roots are. Why we want to do this? Why we want to do this? Take a look at this. When you have the response of a system, let's say this is when the roots are in here, let's see, let me change color so that you have let's see, here we have alright. When k is equal to 0, you have these roots, and then you have one that is in here -2, let's say. When the roots are over here, the response of the system is just like this, oscillates forever. When it's over here, the response might do this. But when it's on this other side, the opposite happens. The system would do this, see? And it'll blow up. So this is you can say all oscillation. This would be unstable. And this would be a damped system. Yeah? So you want to stay on this side. You do not want to go to the other side. See? So this is the place where things would be a stable system, normal system. You would say normal operation. And on this side you will have unstable behavior of the system. So you could say conclusion, you could say for normal stable system, the roots at all times should be like s equal to minus a number, you know, like this, or s equals to minus a plus or minus, this would be the imaginary axis, which would be like this. So these are the kind of roots that we want for a normal operation of a system. If s is plus, or you end up with one on this side, forget it. I think your system will be will need not be stable. So what Professor Evans said is, he says, let's find out these crossing points. And to do that, after his concept came out in the IEEE, people made all kinds of rules how to make these plots, until MATLAB came around and we said, why don't you just give me the transfer function and I'll give you this plot. In fact, that's what I'm going to do just this minute. Let's just go to MATLAB, give the transfer function and do that. Because when those of us who are teaching nowadays learn this stuff, I had to do it on graph paper. And I had to learn the 11 rules to get this plotted down. So now I, comfortably come to MATLAB and I give it the transfer function, and then I'll ask it to give me those crossover points. So why don't we do that now? I think that would be very nice to just see it in real life. Let's just go live to MATLAB over here. And like I said, it does not matter which way you got the transfer function. Whether the block diagram method or the bond graph method only are tools for you to get these transfer functions. So now it comes to the real test. Given the transfer function, what are you going to do with it? And MATLAB has so many nice tools to do this, and so does Simulink. So that's why it's important that we know how we obtain a transfer function and what do we do with it. So why don't I just go and do one exactly like I had it on the explanation in here. So the only thing is just let me just make the font a little bigger so everybody can see good. And yeah, okay, so why don't we define the denominator of the transfer function as I think we need to use the square brackets if I'm not like this. Let's say this is number 1 in here, and the denominator of the transfer function is going to be the polynomial I had in here. Remember this guy here? So s squared minus 2s plus 0. That's what I was so this would be a 1 in here, and then a 2 in here, and then a 0 over here, and that is going to give me that defines the denominator. So now the transfer function g, you put transfer function because the MATLAB needs to know what to do, and then see how nice it is now. It helps you to build the command. It's really cool. So if you do this, this is your transfer function, right? And so you know what I just say, you just say our locus of this transfer function, and look what happens. I was thinking for a little bit, and then it gives me this plot. See, I think we need to learn to interpret this. You see, this is the original one, and this was the initial value also of the -2. Do you see there's the -2? So it, for this particular one, if it says the root locus in here, see it has the let me see how it looks if we do it bigger. Yeah, that's better. See here, there's the little thing for 0, and there's the other one. As k increases from 0 to infinity, I believe in MATLAB you can click in here and find out what the value of k is. That's, yeah, see here, the gain is 0.89 in here, but let's see the gain over here. Gain is 1.35. So this root, as k goes higher, comes this way. See the blue line, and the blue line continues like this, and this one, which is the green one, comes this way as it increases and goes like this. So why don't we just follow, let's just follow the blue to see what it is. Seeing here, this gain 0.35. Let's try here. Just double click on the line and they'll give it to you. This gain 1, but here you see, gain of 2 something. We'll do other transfer functions so that they will look more interesting, and see, it tells you, see, the pole is pole are also another word for the roots, okay? Don't get any confusion about that. See, it says -1 plus 1.3i. This is the -1, and this is going to continue on to infinity. And on this one you see is the other root. But what makes it interesting is when this line crosses the axis. That's what we want. We want to see that. So let's take a look at other transfer functions that I had in my my little plotting here. See, this is a plotting here where that shows, you know, the two roots come this way, the other ones go this way. Here's another one. Okay? You propose a closed loop system, you can have one like this. See, these are the original roots when k is 0, and it never crosses in this case. Let's see if we can find others. Possibly this one, but let me see the transfer function. I think there are some plots in here of a different type, and let's see if this will we do it. Yeah, see this one in here, if you have one like this, you'll produce a root locus like this, and what happens is you have the original roots, and as k goes to infinity, this is the point where you are interested on, is this crossover point. The moment you cross that then you know that you are in a little trouble. There are several ways of doing this. As you can see, you can define the polynomial as the transfer function, and then you can get these plots. Let's see if we have other. These are for different plots, different transfer. This is a good chart, because in here it shows you if you have one of this form, you will get this. If you have another one of this form, you will get this. And if it has this form, this is what will happen. And so we could modify our system to see what it does. See, here's one with 3. I think what I'm going to do more, I'm just showing you several of this, but let's go back to our system itself and change the value of the of the denominator, which was like this, and I could just define this. Let's just change this to 1 and 2 and a 1 and see what it does. Wait, what did I do in here? Denominator is equal here. Yeah. And then I will do the same definition of of the transfer function. See, this is a new transfer function now, and then I will ask it to plot, and then see what the computer does for me. This is a different plot, still not too interesting. Let's see if I to make sure they did what. Yeah, that's the one. But let's just change the denominator. Let's go one order more. So denominator, let's say we put another 1 in here, and then we define the transfer function. So this is our transfer function. So I'm trying different ones. So what would be the plot in here? We need to see what MATLAB did now. See now, this is very different. This system, when you have this polynomial, that's exactly what I told you. You cannot increase the value too high, because right here the system would become unstable. And that's the idea behind this root locus plots, is to design the controller in such a way that it does not become unstable. Or there's other method, other questions to be answered. Where do we put the poles to make it do what we want? And with that, we'll close this concept of the root locus.